Thank you for joining this lesson. Kindly subscribe to this channel. We are going to study mutual induction. Just before we continue with mutual induction, it is good we do a recap of what electromagnetic induction is. We know very well when a conductor is moved in a magnetic field, an EMF is induced. That one is known. When a conductor moves or is moved in a field, a magnetic field for that matter, an EMF is induced, which in turn produces an induced EMF, an induced current. So, for an induced current to be produced, then there must be some relative motion, either conductor moving in a magnetic field or a magnet made to move across a conductor. At least there will be some electromagnetic induction. So in this case, we are going to apply that concept. And what we will do is that we are going to first of all close the circuit. You close the switch so that the circuit is complete, and observe the galvanometer. Then again, we also open the switch, and again observe the galvanometer. So what happens here is that I'll first of all state the observations, then later on I'll be giving detailed explanations on the same. So when it has been closed, we usually say that the current or the galvanometer deflects to a maximum, then back to zero, then back to zero. And when the switch is open again, this is when switch is closed. When switch is closed, then when it is opened, the galvanometer deflects in the opposite direction. Then it is good to note, that the deflection when the switch is opened is greater than when the switch is closed. We are trying to say, when we close this switch, the deflection which is going to be seen in the galvanometer is smaller compared to that seen once we open the switch. So this is what happens. When the switch is closed, current flows and builds from zero to a maximum, and in the process, this iron core, preferably used, iron core, this is where the primary wound or the primary coil has been wound. Therefore, the iron core gets magnetized easily. So within a short time, current builds to maximum, magnetizing the iron core. And when the magnetized iron core, because it is connected to the secondary coil, then we usually say that the magnetism flows into the secondary coil. That one is called magnetic flux linkage. Flux linkage of magnetism. So the magnetism which develops in the primary coil links with the secondary coil, and we have EMF induced. So EMF gets induced since the magnetism created in the primary coil links up, or there is magnetic flux linkage between the primary magnet created here and the secondary coil, which is here. Therefore, magnetism flows and an electric current again is generated. So when an electric current is generated, we are saying that the galvanometer is going to deflect then back to zero. This galvanometer deflects back to zero because once magnetism occurs fully, or once this primary coil is fully magnetized, there is no more flux linkage. So because we said there must be some relative motion, either this magnet going to the core here or the core being brought close to the magnet. And for this matter, the increasing current, which in turn increases the magnetism, behaves as though it is the primary coil, which is a magnet for this matter, being brought close to the secondary one. Therefore, because this one is having a developing magnetism, it behaves as though it's a magnet being brought close to the secondary coil, and that is why there is an induced EMF. On the other side, we are saying when the switch is off, the deflection is going to occur in the opposite direction, and the deflection in the opposite direction is now greater than the one we witnessed when the switch was put on. Why does it become greater? It becomes greater because when the current is cut, the magnetism in the soft ion core now has to die, and the dying off of the magnetism takes a shorter time than the time it took to develop. So this means if we are taking the building up of the magnetism as though it's a magnet being pushed into the secondary coil, and the dying off of magnetism as though it is a magnet being pulled away, whatever we call flux linkage, we said that the rate of magnetic flux linkage is directly proportional to the induced EMF, and right away it will be directly proportional to the induced current. Therefore, the bringing of the magnet is now being slower than taking away of the magnet, since the dying off of the magnet is being faster than the building up of the magnet until it is fully magnetized. Therefore, that difference in time taken by the magnetism to build up and the magnetism to die off is what brings about the difference in the current recorded when switch is on and the current recorded when the switch is off, because of the very fast magnetic flux linkage in the pulling away of the magnet, which is represented by the magnetism dying, and the building up of the magnet, which represents a magnet being brought close to the secondary coil. Now we are having different deflections, and where the magnetic flux linkage is faster, then there we will have the greatest induced current. Thank you for following. Subscribe to my channel and share the link.